Howdy y'all, my name is AFontes, and for my photogrammetry article review I chose an article titled Mapping Snow Depth from Manned Aircraft on Landscape Scales at Centimeter Resolution Using Structure from Motion Photogrammetry. I chose this article due to the fact that our friends on the East Coast have been getting so much snow over the past few days. This snow depth analysis, kind of as an intro, was done due to the fact that there are a lot of health and hazards that come along with snow depth and snow buildup. Some benefits, obviously, being providing drinking water when it melts, along with crop irrigation and the snow depths and consistency, allowing for wildlife dependencies to be met, and then some hazards being avalanches, floods, and geophysical instabilities. Measuring snow depth using photogrammetry had been previously attempted a multitude of times, but it kept on being put to the side because the technology had not caught up with the research being done. Previous attempts tended to be cumbersome, expensive, and really not that accurate when it came down to it. So now that there have been said advances in technology in cameras and flightability and photogrammetry processing softwares, it has allowed for further review of snow depth analysis, which is the basis of this article. So basic photogrammetric methods and approach from this article were to analyze the snow depth of a few different project locations throughout Alaska. So they basically, to achieve these depths, they would collect and compare seasonal temporal data sets by basically taking and collecting photogrammetry of an area, in the summer where there's no snow, and then going and flying over the exact same area and collecting data of the same area but with snow. Take those two imagery sets, turn them into DEMs, subtract the elevations, you get a DDEM, so a difference digital elevation model, and that difference technically should be the snow depth in that area. And then they would also take this DDEM of the area and compare it to other collection methods, such as previously collected photogrammetry and data sets, along with especially truth testing, so grab samples and depth measurements by hand. So in this example you can see at the top, so photo B, from the article you can see a DEM of an area where I think this is like middle of June or July when this imagery was collected, when this flight plan was flown. You can see there's just a little bit of buildup of snow here on the left in image B, and then the rest of it's is generally barren. And then I think the far left there is a small little river valley, and then in image C it kind of looks like it's not an image, but it's just all covered in snow. So they would take these two DEMs, put them over each other, so overlap them, and then you would get this, a difference DEM showing the elevation differences for those areas. So in the blue area, so that kind of tundra area on the right, not really seeing that large of a buildup. But then when you're starting going into this river valley and then into the river valley, you start getting a buildup of up to, I think there on the right it says 2.25 meters of snow along the edge of the river valley. So that's the basis of this research. So equipment and software used. The photogrammetric software used was an Agisoft photoscan software, which, the important key about the software was use the structure from motion algorithm, which is kind of a popular photogrammetric algorithm used to obtain point clouds from topographic points imaged multiple times. So basically, it does not need, like it says up in the top right corner of the slide, it does not need an IMU, because the software has the ability to rectify the image based on points on the ground that have been imaged multiple times from different locations, because of the overlap in the flight path. So the software has the ability to create a point cloud from those like locations, or based on those like locations. And then another notable aspect of this research was the whole process was done using a consumer grade digital single lens reflexive camera, so a DSLR, just a basic Nikon D800E. So that was kind of the notable thing about this research, was it was done using a camera that was about $3,000, whereas usual photogrammetry cameras are, hundreds of thousands of dollars. So making this process more user-friendly and economical. Then image processing was done using software called Adobe Camera Raw. So it allowed for the researchers to take really high exposure photos, so raw high exposure photos, to collect high reflectivity of the snow, along with the shadows that are related in topography. And so this software allowed for the referencing of and the processing of all these images, along with all these different brightness scales coming from the snow all the way to shadows. And then the GPS used was just a simple Trimble 5700 receiver, capable of about 5 centimeter accuracy. The timestamp and the position were connected to the camera's flash, to kind of integrate the camera's flash with the GPS string, making sure your timestamp is for the photos are connected to the location stamp from the GPS. And then again, the GPS ground truths were used to confirm accuracy of position of the photos. So basic process overview was they would image the same location twice, once with snow cover, once without snow cover, or vice versa, and then they would use 60 to 80% overlap of ground coverage to assist with the structure from motion algorithm used in the photoscan software. Then they would run the imagery through the software, the photoscan software, and would use it would geo-reference the imagery, allowing for gridding to create a DEM surface of each set of imagery, so that it can be overlaid on top of each other. And then one DEM would be subtracted from another DEM, so one with would be subtracted from one without, and then you would get the difference DEM, and then that's used to compare against other photogrammetric processes and specifically the ground truth data sets. So this is another image of what you would get. This is of Fairbanks International Airport. This is the DEM, so the difference DEM of where you can see the blue is the runways where it's been cleared off consistently, but then you can see the buildup of snow in the areas and the differences. Specifically, you can even see the planes that have moved based on the differences in the two DEMs. So you can kind of seeing the higher buildup of snow there in red, and then middle is the yellow and green, and then the areas that have been cleaned off, obviously the blue. So results, the maps slash data set accuracies of what they collected. The snow depths were accurate up to, or about to, plus or minus 10 centimeters of the ground sampling data, an example of the ground sampling process you can see there in the bottom left. And then the depth accuracies got as low as 6 centimeters. So I think that's pretty impressive and quite notable for the accuracies they were looking for. And then positional accuracies, they were about 3 centimeters, both horizontal and vertical, of ground truthing positions. So in conclusion, this study used consumer-grade equipment and relatively low-cost photogrammetric software to map and analyze snow depth. The practice presented can be easily replicated and utilized for mass measurements of snow depth. So this process, due to the fact that it can be replicated, means that this process should be and could be applied both on large scale and small scale snow depth analysis projects and research. Personally, just because of some of my interests, I think that this process should be utilized to analyze snow depth in populous locations, so areas of high population, specifically to find anomalies in snow depth, to help predict and monitor avalanche activity. So thank you so much for listening, and I hope you all found it interesting. Thank you.